Good afternoon, everyone. I extend to you a very warm welcome to today's session. I sincerely hope that all of you are in the best of your health. I am Khwahish from Economic Times and your host for today's session. Today's discussion will be on the topic Designing Efficient Electric Motors with Multiphysics Simulation, organized by COMSOL and ET Auto. Before we get started, I would like to take a couple of minutes to set the context and then bring in our speakers to get the discussion rolling. In the global mobility industry, the shift towards developing electric power transport has created an agile approach in R&D of electric motors. Multiphysics simulation reduces the need for physical prototyping, enabling engineers to perform quick iterations at a fraction of the typical cost. In addition, simulation makes it possible to obtain accurate results by combining the different physics phenomena that occur when a motor is running into a single model. In today's session, we explore the power of simulation and see how to design high-performance electric motors. And to enlighten us further on the topic, we have with us today Dr. Rahul Bhatt, Senior Applications Engineer, COMSOL. Welcome, gentlemen. And with this, I kindly request Dr. Rahul to take over and lead the discussion forward.
Thank you, Khwahish. So welcome to the session on designing efficient motors using multiphysics simulations. My name is Rahul Bhatt and I work as an applications engineer in COMSOL, India. So this is the agenda of my talk. I will share some case studies from industry, how industry benefited through multiphysics simulations and how they solved their problems and speed up their design processes. Then we will talk about electromagnetic modeling of the motors. So that is where we start. And then we go on to the thermal modeling, so temperature rise and its effects on efficiency. Next, we have a look at the structural and acoustics coupling, so you can analyze the vibrations and noise produced by the motors. Then finally, we'll take a look at the design optimization of motors. Then I will show a live demo in which we will model a permanent magnet motor. And then we'll have a Q&A session. Okay, to start with, let's have a poll to understand the audience. So let us know whether you are a regular user of simulation tools or you're evaluating simulation tools for your ongoing project, or you're attending out of personal interest, or you're completely new to multiphysics simulation. So first, I'll give you a brief introduction to COMSOL. So COMSOL is a simulation software which allows you to model real-world devices and phenomena. Now it is based on a finite element method or FEM. Any physical phenomena is governed by differential equations, and FEM converts differential equations into a set of linear equations, or you can say matrix equations, and solves them using numerical methods. Now, the strength of COMSOL is the multiphysics. So, for example, if we take a motor, so we'll start with the electromagnetic analysis to understand, let's say, the torque ripple, the cogging torque, the losses. But the losses will in turn cause heating. So, you'll need to couple the electromagnetics with thermal analysis to get the temperature rise. Now, the temperature rise will have certain effects like thermal expansion. So, it may cause structural stresses. So you will do a coupled electromagnetic thermal structural analysis. Similarly, if you want to analyze the different cooling conditions or cooling methods, then you will couple electromagnetic, thermal and fluid dynamics. So the strength of COMSOL is that it allows you to couple n number of physics so that you can predict the performance of your motor accurately, motor or your rotating machine accurately. Next, if you want to write your own equations, which are not there in the existing interfaces, you can do that through equation-based modeling. So you can incorporate that along with the other physics. Then for design optimization, so you need to balance several performance requirements. So in that case, you can perform multivariable optimization. Then you can also integrate your simulations with other CAD tools like SolidWorks, Pro Engineer, and so on. And you can also perform co-simulations. If you want to do a system level simulation, you can perform co-simulation using MATLAB and Simulink. Now, once you have built a model, COMSOL has a unique feature called Application Builder. So once you build a model, considering a target user, you can create a customized user interface, which has the input parameters of interest, the output parameters of interest, the results of interest, and you can generate an app or the customized user interface, and you can share that app with other users. So once the other users have that app, they can modify the input parameters, run the simulation, and see the results of interest without worrying about the intricate details of the simulation, like what is the meshing or what are the boundary conditions and so on. So this allows you to easily coordinate between different teams. So we'll see that further in our case studies. Okay. Now this is the graphical user interface of COMSOL. It basically consists of three parts: the model builder window, which has all these steps which you need to perform for performing any simulation. So whether it is a single physics or multiple physics, the workflow remains the same. You need to go through these steps in sequence. So first you either build the geometry, or you can import the geometry from other CAD tools. Then you assign the materials. Then you specify the boundary conditions. Then you do the meshing. Then you perform study steps such as stationary, time dependent, and so on. Finally, you come to the results analysis and post-processing. Now, the second part is the settings window. So if you click any node in this model builder, you will see the corresponding settings over here. Alternate to the model builder is the ribbon. Here you see, so which also has the same steps which you need to perform for any simulation. So this is just to alternate to the model builder. Then you have the graphics window, which shows you the geometry, the meshing, the post-processing, and so on. Next, we will have a look at some case studies from industry, how they benefited from multiphysics simulations, how they could improve their designs, and how they could speed up their design process. So this is a story from case study from FZB Technology USA. They wanted to design an electrohydraulic power steering system in which the hydraulic fluid was pumped by a motor. Okay, this is the PMM motor which was driving the pump. Now they wanted to study the performance of the system under extreme loading conditions. So for example, if there is a sharp turn or the wheels are stuck, then in that case, a large torque needs to be applied onto the steering wheel. So the pump has to work harder, and so the motor draws a large current and it gets heated up. So they wanted to know the behavior of the system under such conditions. So they performed a coupled electromagnetic thermal structural analysis of the motor. And in their simulations, they found that under extreme loading conditions, the thermal or structural stresses due to the thermal expansion in the stator exceeded the yield limit of the stator material. So basically, the simulations were predicting failure of the stator. So from this knowledge, they modified the design and they introduced these axial grooves, which you see over here. So these axial grooves allowed for the safe thermal expansion of the stator while keeping the stresses within limits. So in this way, they used multiphysics simulations to create a robust design of the motor. And this is a case study from Volkswagen. Now, they wanted to optimize their designs of the electric drives. They faced two challenges. One is balancing the different requirements. So, for example, the magnetic utilization requires that you need thinner web-like structures, okay, for your motor. But then durability requires that you require stiffer, thicker structures. That is one. And second thing, they wanted to coordinate between different teams like simulation, design, testing, and so on. So what they did is they built a model which performed electromagnetic structural analysis of their rotor laminations, which you can see over here. And they created an app. So this is a screenshot of the app. So they shared this app with other teams like design team, testing team. Now, once the other teams had this app, they could vary the parameters like the geometry, the material, the loading, and they could run the simulation and see the results. So they could quickly coordinate between different teams. And that is how they increased or basically expedited the design process. And as a result, you can see Castle plant produces 150 electric and 300 hybrid drives every day. So these are the two case studies which I wanted to share. Now let us get into motor modeling, and we'll start with electromagnetic modeling. So here we see the different features or functionalities which you can use to model your rotating machines. So any rotating machine consists of basically 4 parts or 4 elements. You can say the rotor iron, stator iron, permanent magnets, and stator coils. So let us see the different features. So for modeling the coils, you have single conductor and multi-turn coil domain features. Then you can model the laminated iron of the stator. You can use sector modeling to simplify your simulation. So you can reduce the computational complexity without compromising on the accuracy. Then for computing the torque on the rotor or the cogging torque on the stator, you can use the torque calculation feature. So these features make it very easy for you to model the motor. Then for modeling the materials, you can model hard and soft magnetic material. You can model the magnetic saturation so that you can optimize your magnetic utilization. If you want to calculate the losses, you can do so by modeling it as as providing complex permeability. You can also model the temperature dependency of material behavior. So we'll have a look at that in more details in coming slides. Now, this is an example of a permanent magnet motor, which finds a wide variety of applications. Now, due to large power density, it can be a traction motor in electric vehicles, or even in conventional automobiles. It can be used in, let's say, power windows or the coolant pump. It has a variety of uses. So this is an example of a PMM motor. So we start with the modeling of the motor from the geometry. Now, COMSOL provides you a part library for permanent magnet motors. So we have a 2D part library, which is fully parameterized. So this is an example of a PMM geometry. And there are 3 variants of the rotor. So you have surface mounted, interior magnet, and basically 2 variants of interior magnet rotors. And this template is fully parameterized. So it makes it very easy for you to create the geometry and customize it to your requirement. So now we start with the template of the geometry. Then we do the electromagnetic analysis. For modeling rotating machines, COMSOL has rotating machinery magnetic interface, which allows you to very easily model any kind of rotating machine, whether it is permanent magnet motor, BLDC, or induction motor, or switch reluctance motor. Then you can get the predefined variables, which will allow you to easily assess your motor design. So something, for example, radial force density, or your forces, or the torque ripple, or azimuthal force density, and so on. Now, to make it easy for you to learn simulation and learn how to do the simulation of rotating machines in COMSOL, there are tutorial models. So for example, PM motor 2D. So this is a 2D model, and this is a 3D model. So you can have a look at these models, which will allow you to learn the simulation using the rotating machinery magnetic interface very easily and quickly. Then we have a look at the material modeling. So if you want to model the ferromagnetic material behavior, you can model the BH curve. Basically, you can specify the BH curve. For frequency domain analysis, there's an effective BH curve model in COMSOL. Then if you want to model the losses, magnetic losses, you can specify complex permeability. If you want to model the BH loop, so there is the Giles-Atherton hysteresis model. Then in addition to that, if you want to model magnetostriction, even there is a ready-made coupling in COMSOL, which allows you to easily model magnetostriction. In case of a motor, particularly PMM, mostly it is the case that the Lorentz forces and reluctance forces are much higher than the magnetostriction. But yeah, you can incorporate or analyze magnetostriction in addition to other forces. Then we started with the electromagnetic modeling. Then we come to the computation of iron and copper losses. So for modeling iron losses in the stator, you have three options. So you can use the empirical models like Steinmetz and Bertotti loss formulae, or you can have a fully user-defined model. So for example, if you have the loss curve from your manufacturer, you can also incorporate that in your simulations and you can get the iron losses. Now, this is a snapshot of the loss calculation feature, which allows you to easily calculate the losses. So we have started with electromagnetic simulation. Now let us go on to the multiphysics. So we would like to understand what aspects of motor modeling would you be interested to analyze. So please let us know your inputs. Please launch the poll. And meanwhile, if you have any questions, please type them in the Q&A tab. Okay. So we'll take the questions in the Q&A session after the demo. Okay, please let us know your interest, whether you're interested in losses. Yeah, okay. Thank you for your inputs. So let us proceed with thermal modeling and efficiency. So we started with electromagnetic modeling. The natural result of the losses is temperature rise. So in COMSOL, you can model the temperature dependent material characteristics. So for example, due to temperature rise, the conductivity of the copper would reduce. So that you can model. Then in addition to that, the remnant flux density of the magnets would reduce because of the temperature rise. So such kind of temperature dependent material behavior can be modeled. Now it is important for you to know that normally what you do is you will do the electromagnetic simulation and then you will couple the electromagnetic losses with the thermal analysis. So that will give you the temperature rise. But this feature allows you to do a fully coupled analysis, which means that because of electromagnetic losses, there is temperature rise. Because of temperature rise, there is a change in the conductivity of the stator coils. So this you can model. In addition to that, the temperature rise will also cause reduction in the flux density of the permanent magnets. So that also you can model. You see here the interpolation function. So you can model the remnant flux density as a function of temperature. So that is what is being shown over here. So this fully coupled analysis allows you to accurately predict the behavior of your motor and accurately predict the efficiency. So first part is, of course, you can do a thermal analysis and you want to examine it for different cooling conditions. So that you can perform the simulation for different cooling conditions such as natural air convection or forced air convection or water jacket cooling like this. And you can compare the temperature rise. So for example, in this case, the temperature rise with natural air convection is 162 degrees Celsius. With forced air convection, it reduces to 108 degrees Celsius. So in this way, you can do your simulation for various base speeds, for various cooling conditions. You can compare them so that you can choose your cooling method and you can optimize your design. The natural effect of the temperature rise is on the efficiency. So this is one thing which is a very important factor to understand. So once you extract the efficiency map, so this is example of efficiency map at ambient temperature, which means that the fully coupled analysis here hasn't been performed before extracting the efficiency map. Now here you see the efficiency map, and we'll see the difference a fully coupled analysis has on the efficiency map. So once you consider the effects of temperature rise on the torque and the conductivity of the stator coils, you see the efficiency map changes. So the shape of the efficiency map changes, the distribution of efficiency changes. Here you see that at the same stator temperature, the torque is reducing with speed, okay, because of the temperature rise effects. So, I mean, you will design your motor for a particular operating point, but when you run it at your operating temperature, if the efficiency distribution is changing, then your operating point will shift. So you want to predict it before or while designing it. So for that, you can do a fully coupled analysis, and you can predict the efficiency map accurately along with the temperature rise effects, so that you can plot your, let's say, drive cycle, and you can predict the efficiency, which will allow you also to predict the range more accurately. In addition to that, you can have a temperature map. So here you see a temperature map is basically the average stator temperature for different speeds and torque values. Now this is with natural air convection. Okay, you can also extract such a map for different kinds of cooling conditions like forced convection or water cooling. And here you can see that at different operating points, what will be the average stator temperature. Now this will allow you to know the temperature, and you can choose the insulation class and also the cooling method. So this will make your design, facilitate your design and allow you to choose the optimum design for your motor from different points of view. Okay, so now we have had a look at electromagnetic thermal analysis. We'll proceed to the structural acoustics. Now, here is one example of induction motor, which has a non-uniform air gap. Because of this non-uniform air gap, there are unbalanced electromagnetic forces which act on the stator and the rotor, and they produce vibrations. So we start with the electromagnetic analysis. We get, here you can see the magnetic field, how it varies, how it changes as the rotor speeds up. From the electromagnetic analysis, we extract the forces, or basically force components. And here you see the force pulsating components of the force, basically which cause the vibrations. So these electromagnetic forces we will couple to the structural analysis. So the structural analysis will compute the stresses and the deformation. And you can also see the, so this is showing the rotor orbits, which means the displacement of the two ends of the rotor shaft due to the imbalance in the air gap, and also resulting displacement due to the unbalanced forces. So you can see the rotor orbits, basically two ends of this shaft. So in this way, you can perform electromagnetic structural analysis. Going one step further, these vibrations are going to produce noise. So you can couple the deformations. The deformations, or you can say the surface normal acceleration, is what is going to cause the sound waves. Okay, so you couple the structural deformation with the acoustics, and you can see how the sound pressure or the noise is produced by the motor. Going even one step further, you can extract this Campbell diagram, which gives you the different frequency components, okay, in the noise produced by the motor at different motor speeds. Okay, so this will actually allow you to generate a sound file. I mean, you can extract a sound file, and you can actually hear how the motor noise sounds. Meaning you can simulate the motor, do a coupled electromagnetic structural acoustic analysis, and you can actually extract the sound file from the simulations, how the motor noise sounds. Okay, that is possible in COMSOL. And we have examples in our application library, which we can share with you. So now we have taken a look at the different multiphysics analysis of rotating machines. In addition to that, even it is possible to model linear motors. So presently, these are a very important topic of research and development, since they find applications in hyperloop, or magnetic levitation and similar applications. So you can also model linear motors very easily in COMSOL. There are specific features which allow you to model the linear motors, like periodic conditions. And we also have examples in our application library, which you can have a look at, and you can easily learn how to model such motors. Then we come to the final topic, which is the optimization. So once you have analyzed the motor, but the final goal is that you want to optimize the design, considering the different constraints, physical constraints and performance constraints. So in COMSOL, you can perform parameter optimization or shape. So, okay, I'll tell you what is parameter optimization. So this is, so the shape and the basically profile of the machine is fixed, but you can parameterize the geometry. So for example, the height of the magnets, the width of the magnets, the air gap, the diameter, and so on. So you can vary the parameters and you can optimize your design for a particular objective function. So something like you want to maximize the torque, but you want to find the exact combination of parameters which will give you the maximum torque for the same amount of material. So such kind of analysis you can perform in COMSOL. Then you can also perform shape optimization. So the shape itself of the machine geometry is changed and optimized so as to give you the optimum objective function. Topology optimization means basically the material distribution in your machine geometry that can be optimized. So you can automatically, the software automatically does it for you. And here you see one example. This is axial flux motor in which the torque is being optimized and the shape of the magnets is being changed. So for this shape, it will give you the maximum torque. Okay. So this will make it very easy for you to optimize your designs from different points of view. Then you can incorporate multiple physics in your optimization. So electromagnetics, heat transfer, structural mechanics. So your problem definition could be you want to maximize the torque with minimum material, but you want structural endurance at high RPM. So such kind of problem you can easily solve. And the COMSOL optimization module allows you to do that. Yes, so we have come to the end of the presentation. Please keep typing your questions in the questions tab. So we will go on to the demo now. Okay, so this is the graphical user interface of COMSOL. We begin with the model wizard. So there are different options. So depending on what kind of modeling you want to perform, 3D, 2D axis symmetric, 2D, and so on. So right now we choose 2D. Then there are various interfaces over here. We will choose the rotating machinery magnetic. Now, when you add a physics interface over here, the corresponding dependent variables you can see over here. So basically what this is telling you is when you do the simulation, the output of the simulation is going to be these dependent variables. So these are the output variables of the simulation. Then we add the stationary study. Okay, so now here you see the graphical user interface. So we begin with the geometry. And as I told you, so COMSOL offers you a part library for modeling permanent magnet motor. So we will use that part library. We'll add a rotor, surface mounted rotor. And then we will add stator. Just to show you the variants, you can see the variants available over here. And the stator, we'll add the stator. Okay, so we will model a 6-pole 9-slot machine. Okay, then the stator. So we'll have 9 slots. Here you see the geometry is formed automatically. Then the final step. So whenever you are modeling rotating machines, the final step is form assembly. So we'll click build all. Okay. Next is we add materials. So here you have two options. You can add materials from the material library, or you can add a blank material and specify your own material property values. So first we will add air. So by default, the first material which you add, that gets assigned to all the domains. Next, we will add the soft iron for the stator and the rotor. So here I will assign it to the rotor and the stator. Okay, so the rest of the things, we will model through the, for example, the stator coils and the magnets. Those will model in the physics interface. Okay, we also want a partition here. So I will just change this. So you can fully customize the templates for your requirement. So we'll make it slot winding type 2. So we'll have this partition. Okay, so this is geometry is formed and we have assigned the materials. Next, we'll go to the physics. So I will add Ampere's law. Now we'll model the stator and rotor iron. So I'll choose the iron and we will specify the, here you see there are various options for the magnetic material behavior. For linear material, there is relative permeability. Now we'll choose pH curve. We also want to calculate the losses. So here I will add a loss calculation feature. And here you see there are various options. For non-magnetic domains, you can find the losses due to resistive heating, or you have these models, these empirical models for iron losses. You can also have a user-defined loss model. Right now, we'll choose Steinmetz. We'll leave the constants of proportionality here as they are, the coefficients as they are. Now we'll model the magnets. So I will first choose 3 magnets, which are magnetized radially outwards. Okay, I'll just, okay, you can see this. Here we choose the remnant flux density and we specify the recoil permeability and the remnant flux density. So let us say this is 0.5 Tesla. And we want it magnetized radially outward. So I will add a coordinate system here. I'll add a cylindrical coordinate system and we'll use that to model the radially outward magnetization. So here I will choose in the magnet, I will choose cylindrical system and I will, So here you see now this has become R phi Z. So this is magnetized in the R direction. Similarly, I will duplicate this and I will select the remaining magnets. These things remain as they are. I'll just change the direction of magnetization. Okay, so the magnets are modeled now. Next, we model the coils. So I will choose the coil feature. And we want to model the 3 phases. So here in the settings window, you can see the various options. Here we will choose homogenized multi-turn. Since these are in series, we will click coil group. Right now, we'll just open circuit the coils and we'll see the induced voltage. We'll leave the number of turns as it is. Here you see a coil wire conductivity. So this corresponds to copper. Next, you can choose the coil wire cross-section area by various methods. Like you can specify this directly, or you can specify the wire gauge or the conductors, or even the round wire diameter. Right now, we'll leave it as it is. Next, we specify the reversed current direction. So it's like the current is going from one side and it will come from the come out from the other side. Okay, similarly, we will model the rest of the phases, B and C. So I will just duplicate this. I will clear out the selections, domain selections, and I will select these. So these settings remain as they are, okay, these ones. We just need to change the reverse current direction. So for this, we will select 1, 2, and 3. Similarly, the third phase. I'll just duplicate this. I will clear this out and select the remaining coils. And again, reverse current direction. 1, 2, and 3. So now the coils have been modeled. So we have modeled the iron, the magnets, and the 3 phases of the stator coil. We want the torque. So I'll add a force calculation feature and I will choose, okay, we want the cogging torque. So I'll choose the stator, okay. Now this will automatically generate inbuilt variables, which will give us the cogging torque. So now we want to model the motion, rotatory motion. So we'll add a rotating domain, moving mesh, rotating domain. We'll choose the rotor domains. So this is going to be rotating. So we'll specify it, give it a rotational velocity. And let's say 2 pi. So it's like 1 rotation per second. So now this is set up. So I'll just go over it. We defined the geometry. Then we added materials. Okay. Next we specified the physics. So the magnets, iron, and the coils. And for the torque, the force calculation. Now we come to meshing. So you have 2 options. You have physics controlled mesh with predefined sizes like normal, fine, extra fine, and so on. Or you can have a user controlled mesh. So this user controlled mesh allows you to control the mesh size in each domain or boundary or surface and so on. It gives you full control. Here what I'll do is I'll just refine the mesh of the stator a bit more. So I will change this to domain. I will choose the stator domain and I will make this as, let's say, finer. Okay. So now the meshing is also done. Now we need to add study steps. So first is stationary. Second, so we'll add study steps, time dependent. And this, let us specify the range as 0 to 1 second with, let's say, 51 steps, time stepping. And we also want to calculate the losses, the iron losses. So I will add time to frequency losses. So basically this does the FFT, Fourier transform of the flux in the stator and rotor, and it computes the losses. The average time loss average iron loss in 1 electrical cycle. So here we'll use a user defined, so 0 to 1 second. And you can also specify the number of harmonics you want to consider. So 6 harmonics are sufficient. So now we can solve this. Is it possible to simulate winding temperature of brushed DC motor? Yes, definitely. So here you can do the coupled analysis of electromagnetic and thermal analysis of the brushed DC motor. So since the multiphysics coupling is the strength of COMSOL, so definitely you can compute the temperature of the entire motor. I mean, all the components. Whether COMSOL will suggest the motor topology based on various input specifications. Yes. So I will just give you a brief idea. When you set up an optimization problem, so you will have an objective function, okay, something like, let's say, torque, and you want to maximize the torque. Then you will have some constraints or control variables on with constraints. So something like some parameters or parameter limits. Okay, so you will set up the problem, and you will also add the relevant physics. When you do topology optimization, COMSOL automatically changes the material distribution in your geometry, and the output of your simulation is the final. COMSOL itself gives you the final geometry with the new topology, which will give you the optimized objective function. Okay, so that is why it makes it very easy for you to do the optimization using the optimization module. Okay, so we have the results. Here you can see the losses. Okay, iron losses here. So these are the time average losses in one electrical cycle. So this gives you in terms of watt per meter cube. But let's say you want the total losses. What you will need to do is integrate over the surface of the stator. And here we will add the expression for the losses, volumetric loss density. Now, this is in watt per meter. So basically, we want the loss, total loss in the machine. We will multiply it by the axial length. In this case, let's say the axial length is 90 mm. We just multiply it by that. And when I evaluate that, you will get the losses over here. So 0.15 watt losses are there in this case. So this is how you can compute the losses in your machine. In case of a 2D model, okay, you can also do a 3D model, and we have examples of 3D motor modeling in our application library, which I can show you shortly. Okay, so next thing is let's observe the cogging torque. Okay, so I will add a global plot. Here I will change it to the time dependent one, and since we added the force calculation feature, the torque is available as an inbuilt variable. Okay. So this is the cogging torque. And I mean, as expected, you can see that the average is somewhere around 0. And here in this case, basically, if you want a smoother curve, you just need to increase the number of time steps. Right now, our time steps are a bit coarse, right? So just need to increase them so that you can get a smoother curve. Next, let us have a look at the induced voltages. So I will just duplicate this. Let's have a look at the stator induced voltages. So here we will go to the global and we will change this. Now, since we have done the coil modeling, the coil parameters will be available over here as inbuilt variables. Here you can see coil current, coil power. This is the flux linkage of each coil, okay? Coil resistance, coil voltage, and so on. So here we want to see the voltages in all the 3 coils. So I'll just add this coil voltage variable, and we can plot. So here you see the 3-phase voltage in the coils, induced voltage in the coils. Next, let us have a look at the magnetic flux density distribution. So I will change this to this, and I will add surface and magnetic flux density. I'll just change. Okay, now if you want to see how the magnetic field changes with the motor rotation, you can see here. If you want to generate a animation, so you can do that also very easily. Here I will choose the 2D plot group 4, and I will click show frame. Okay, here you can see how the magnetic field varies. Now, just a brief, I mean, I would like to discuss just from the magnetic field distribution, you can get a lot of insights. So for example, you see here, the magnetic field is actually not occupying this position. Okay, so if you see in a time average sense, it's never occupying that position. It's less. So in that case, what you can do is you can actually remove material from this part. Okay, little bit of material, and actually the magnetic utilization is going to improve. Basically, with lesser material, the torque will remain the same, but you will have lesser material requirement. Next, you see over here. So the magnetic field occupies a fraction of the cross section of the rotor. So you can actually remove this part and make it into a non-magnetic material. Then if you see, there's a difference in the magnetic flux density over here and here. So if the difference is a lot, like you can see over here, so that shows that there is scope to actually reduce the width of the poles so that the optimum magnetic utilization is optimum. Okay. So in this way, you can get a lot of insights into the machine design just by looking at the magnetic flux density. Okay, now one last thing. Yeah, I think we have gone through all the results. So let us now move on to the question and answers. Okay, so please type your question, whichever questions you have in the Q&A tab. Now we'll have a Q&A session. Okay. Can we add trapezoidal vents on the rotor by uploading AutoCAD drawings into this software? Yes, definitely. So the CAD import module is there so that you can import geometry from any software. Okay, any other, I mean, in any other format, like part or solid part and so on, or from AutoCAD. How can we increase speed of AFM motor? Designing factors for high speed AF motor. See, so designing factors. So this is a very good question. Actually, that is where the strength of simulation comes into picture, and more so multi-physics simulation. So you can do like fully parameterize your geometry and your input conditions like excitation and I mean other inputs, and you can do a parametric sweep, and that is you can see the results like a parametric variation of your output parameters like torque and losses and so on. So that will allow you to actually get a insight into which factors affect the output of your motor more. So that is definitely what you can do using COMSOL. How are you modeling the stator laminates for frequency analysis, and what sort of connection is used between stator and pins? So what I showed you was a 2D example. In that, so the pins aren't modeled. I mean, the overhangs or the pins aren't modeled in 2D. If you want to study the effect of those, you'll have to go for a 3D modeling. Okay, so the geometry itself will be 3D, and you'll have to explicitly model the pins or the overhangs. Then stator laminates. So for getting the effect of laminations, I mean the losses, you can use the Steinmetz or Bertotti loss model. Specifically in Bertotti loss model, it allows you to specify the lamination thickness for your stator material. Okay. When the air gap is increased, the losses do the losses increase in permanent magnet motor? Now again, you can see this. So the simulation can actually make it very easy for you to understand and get insights into your machine performance by doing a parametric analysis. Okay, you can have any parameter, like air gap can be a parameter, and you can see how the losses vary. You can plot a graph. Okay, so that is the strength of COMSOL. Is it possible to simulate solenoid coil design like force versus distance, temperature rise? Yes, definitely. So you can also, I mean, besides motors, you can also model electromechanical devices like solenoid coils. And we have examples in our application library, okay, which you can have a look at. Models which show you how to model solenoid coils. We also have a contactor model, electrical contactor model. So I'll show you that. Okay, we'll show those things on our website. May I know circuit designing is possible in COMSOL? Now, okay, basically it is possible to couple your FEM model with external lumped circuits. So here we have the motor model. Now, if you want to couple those coils or connect those coils to external lumped circuit like RLC circuits, or you want to provide the voltage source from the circuit. So there is an electrical circuit interface which will allow you to couple your FEM simulations with electrical circuits. Parameter optimization process for the improvement of parameters. Can give a suggestion. Okay, the question is not clear, but okay, I'll just like to point out one more thing. Now, there's this uncertainty quantification module. So this specifically is meant to allow you to study how the different manufacturing parameters, like manufacturing tolerances, affect your design. So you can do that for any design. For any motor design, for example. You can first identify the parameters, the major parameters which have effect on your output parameter. And so you can also study how much variation in the input parameters would affect how much variation would occur in the output parameter. So for that, you can use the uncertainty quantification module. Okay. So I'll just show you, I'll briefly show you our website and show you the application gallery which you can have a look at. So some resources which you will find interesting and useful. Okay, so you can have a look at the application gallery, and here we have a different, extensive library of models. If you want to examine motor models, so here we have motor models. We have some benchmark models, then PMM model, finalizing losses, temperature rise, and efficiency. This is basic permanent magnet 2D model. We also have parameter optimization example for electric motor. So you can have a look at these examples, okay? Acoustic structural analysis. Okay, so you can go through this application gallery, which will be, and okay, let's say if I open this, you can actually have a look at the models and the presentation and the tutorial PDF. So this PDF gives you a tutorial. Basically, you can see step by step how you can build this model, and you can learn how to build the model very easily by following the PDF. Okay. Next, we can also have a look at the blog. Okay, the blog is basically, it consists of very useful readable articles. And if I, let's say, type motor, so you can have a look at these articles which explain what kind of different analysis you can perform in COMSOL and what features you use. So this is very lucid and readable articles on different kinds of analysis. So you can also go through these articles, okay? Yeah, any more questions? We have, I think, a couple of minutes more. Is this tool web-based to use for hands-on understanding the modeling and simulation? No, this is not web-based as such, but there's one thing. So when I mentioned apps, so once you, basically there are different ways of deploying apps. From your COMSOL model, you can generate an app, and for deploying the app, you have two options. So one is the COMSOL compiler, using which you can generate a standalone exe file, okay? And that exe file you can share with n number of users. That standalone exe file, does not require a COMSOL license, okay? Second thing is COMSOL server, okay? So you can have the app on the COMSOL server, and that can be browser-based or web-based, okay? So that possibility is there in the app, server-based app, okay? Okay, what more? Let me know if you have more questions. Live testing like loads connecting to the motor is possible, and test torque, speed, temperature in different load conditions. Actually, can you elaborate on that? If you can elaborate on your question, we will be able to address that better. So we would like to know your interests. After this session, would you like to get a trial? You could try a console by yourself. And if you want to connect to a console representative for discussing your project, if you are interested in both, or if you're interested in none of the above, please let us know. What are your interests? So please let us know your interests, whether you would like to try it out. I mean, you can download those application gallery models and you can open and you can learn it quite fast. Yeah, and you can go through those articles. There's also a console learning center which has step-by-step video tutorials on each and every modeling feature like geometry, meshing, post-processing, and so on. Okay, so even you can have a look at those videos. That is called the console learning center. So that will also make it very easy for you to use or try out console. So we have many resources which will help you to work with console and try it out very easily.
Thank you, Dr. Rahul, for such an insightful session. We gathered quite some interesting learnings from the presentation. With that, we come to the end of today's webinar. Thank you, Dr. Rahul, once again for taking out time and being with us today. I hope you enjoyed this event as much as we enjoyed putting it all together. Before we wrap up, Team Economic Times wishes all our audiences safety and the best of health. Have a great evening ahead.